I want to start out acknowledging my co-authors who all contributed quite a bit to this study, as well as some of the funders, most significantly the Woods Hole Oceanographic Institution. So some of you may be familiar with the field of Paleo Tempestology. This field basically attempts to reconstruct records of prehistoric storm frequencies, applying a variety of paleo proxy records. Basically, this work, this field is based on the fact that during large storm events, surging storm waters that breach, overtop, or flow through tidal inlets carry with it sand, which gets draped over back barrier environments. And when buried during more quiescent times by finer sediments, this preserves a record of storm events. Some of the earlier scientists, Emery and Redfield, were the first to acknowledge the relationship between coarse sand layers interbedded in peat and extreme hurricane events in Massachusetts. The study site is located in Waquoit Bay, Massachusetts, which is on Cape Cod. It's a very shallow estuary at a maximum depth of about 3.5 meters, and most of the fresh water coming into the system is through groundwater seepage. This area, being positioned on the south side of Cape Cod, is very sensitive to northward tracking hurricanes and more buffered to extratropical cyclones, extratropical storms. So when we started out with this research, we had a few questions we wanted to answer. This was primarily based on the fact that Waquoit Bay is a relatively unique site to attempt a storm reconstruction due to its shallow nature, as well as the more distal location of the core site way up here in relation to the barrier. So we wanted to ask, is there a storm record within Waquoit Bay, specifically in the North Basin? And if so, what was the transport mechanism to get that coarse sand into that area? We also wanted to be able to use our results to better illuminate and provide context to more recent flooding events. So we applied a variety of methods. We took sediment cores using a vibracore system in about 3 meters of water. We brought those cores back to Woods Hole and grain sized them, scanned them within an XRF, and collected samples for continuous flow AMS. Now, because we didn't really know what the hydrographic conditions were within the bay during hurricane events, we laid out a series of water current meters along the north-south axis of the bay prior to Hurricane Irene in 2011. Now, it should be noted that Irene is a relatively small hurricane system which was quickly downgraded once making landfall to the west of the study site. We also modeled some of the modern and prehistoric storm surges using slosh. I should note that these instruments here, here's the water level gauge and the current meter, were both designed by one of my co-authors, Sheremet. Now, as we look at some of our results, we see our 3 sediment cores, Waquoit 1, Waquoit 2, and Waquoit 3. These cores run, Waquoit 1 is the shallowest at 6 meters, and the other 2 cores are around 8 to 8.5 meters. Now, these cores are dominated predominantly, when we expand here on Waquoit 2, we see that the majority of the sediments in the cores are sandy mud, characteristic of estuarine deposition. We also see the presence of numerous bivalves and gastropods in the core, and we see some, visually, we see some coarse sand horizons running through the core, with some of the larger horizons observed in the lower sediments. And our radiograph, which is an X-ray of the core, shows some of those sand horizons, but also really gets blurred up where you have a lot of shells that also increase the density. There's also an abrupt contact in the deeper cores with glacial outwash, so we feel we collected the entire estuarine sequence there. So when we look at our water level heights during Hurricane Irene, we have about a 0.8 meter storm surge up at the head of the bay, and we see the difference between the water level gauge at the mouth of the bay and the head of the bay. We have about a 17 centimeter increase up at the head of the bay. And this is also observed in our models of the 1638 hurricane event, where, as would be expected, we have these increased storm surges at the head of the bay as that water is pushed in and has nowhere to go and rides up into the uplands a little bit. So our highest modeled surge was for the 1635 Great Colonial Hurricane. This is the largest hurricane to impact the area that's documented in historic records, and we had about a 3-meter storm surge during that event that was modeled. And then the more modern event that's the largest storm to impact Cape Cod in the last 50 years was Hurricane Bob, and we had a 1.62 meter surge during that event. So as we look at our water gauge, our water current data here, on the y-axis here we have velocity, and some of the largest velocities that we found was at the entrance of Waquoit Bay. So here's the entrance, and here's the head of the bay, and here's our transect of gauges. Now at the entrance of the bay, the currents were recorded at almost 1 meter per second, and you can see the tidal impact here, but synchronous with the peak winds of Hurricane Irene, as well as the low pressure anomaly, we had a distinct increase in water bottom current velocity within the bay. Most significantly, if we look at the water level gauge that's in the vicinity of our coring site, we see that there's a dramatic increase in velocity up to 25 centimeters a second that's moving along shore. And we also have this seaward component that is about 10 centimeters a second moving away from the northern shoreline into the North Basin. And this is significant because this is enough velocity to transport sediments from the shore face into the coring site. Now, one of the most challenging aspects in this study was the development of the age model. There's a lot of disturbance because this is a shallow water estuary. So in the upper sediments, there was a number of things disturbing the record. So we were unable to use cesium and lead dating. So we used radiocarbon ages for the long-term sedimentation rate, and we used bulk lead for the historic sedimentation rate. Now you can see there's a distinct change from 1.1 millimeter a year to 8 millimeters a year. And this is recorded in many areas in New England due to the widespread land clearance and agricultural practices that happened after colonization. Now, as we look at some of our grain size data, first I'll draw your attention over here to our bulk lead plot. So here we have a number of pollution-derived chronomarkers, beginning with the start of the Industrial Revolution and the increase in lead being deposited in the sediments, falling after the phase-out of leaded gasoline to a low in 1986. Now, as we filtered our D90 grain size so that we were kind of removing some of the short-term variability and only identifying the coarse grain anomalies most likely associated with hurricane events. Now, we found that when we plotted this out with our age model, that many of these events correlated to either hurricanes that were documented in the historic record or some of the large extratropical storms such as the blizzard of '78 and the Groundhog Day storm of '76. So to identify lower threshold and upper threshold events, we set these thresholds based on, the lower threshold was set on Hurricane Gloria, which was a relatively small hurricane, and the larger threshold was set on Hurricane Bob. So if we look at our prehistoric record, our historic and prehistoric combined, we see that through the record we had 89 lower threshold events and 16 upper threshold events. Now, what I wanted you to see here is the fact that during the prehistoric period, we had much larger and coarser event beds, which may suggest stronger storms in the prehistoric past. Now, if we look at our cumulative frequencies through time, we see that the lower threshold events are relatively steady through time. Here's the Waquoit 1 and Waquoit 2 cores, 2 and 3, and here's the Waquoit 1 core. And there is definitely some fluctuation and variation in the frequency of storms. We also see this dramatic uptake in storm frequencies over the last 150 years. Now, more interesting is these upper threshold events, which during the prehistoric period, we have a really high frequency of these larger storm events. We have a kind of a stable time period, and then we have another dramatic increase during the historic period. Now, one might want to jump to conclusions and pinpoint this increase during the historic period as something related to climate, but we should be cautious with that because remember those deposition rates were very different between the prehistoric period and the historic period, with the sedimentation rates during the prehistoric period, only 1.1 millimeters a year, was really undercounting events, where during the historic period, the higher sedimentation rate is preserving events. So at least part of this trend here, this increase, is related to that fact. So to look at a conceptual model of what we have hypothesized to be one of the primary mechanisms of this sand getting into the North Basin, we have developed this model here where basically this is a commonly known thing. We have our wind-blown waves, we have our storm tide moving against the upland bluff here. And this is a photo of Hurricane Irene. Mean high water is about right there. So we can see that surged water piling up and eroding that upland bluff. Here we have our sediment core site and our sand horizons. And so once that water is up along that northern shoreline, we have it excavating the upland bluff. We have that alongshore current eroding sediments, and we also have that seaward moving bottom current following an energy gradient from this high energy area of the swash zone, carrying that sediment-rich water along that gradient into the lower energy areas of the North Basin, where then this sand is preferentially sorted and deposited into these sand horizons. So as we look to the future, what can we use our results for? How can we better illuminate some of the future flooding risks? We see that many of the risk assessments based on instrumental records are really lacking because of the lack of context of prehistoric events and even historic events, such as this is the 1635 hurricane. Remember, that's the largest to impact this area in the historic record. This storm surged up into Buzzards Bay and caused at least a 6-meter surge. Some put that at a higher surge level. And so this is a catastrophic event. So what happens if this event happens today? So here's New Bedford. So if we had, there we go. So if we had New Bedford, we put that 6-meter storm surge there, and then we have to account for the sea level rise that's happened since 1635, which is approximately about a meter. And then if we look to the future, about another to 2100, we have another increase of about a meter. And so we're up at the same storm hitting today would cause about an 8-meter surge. So we have increased risk due to sea level rise as well as increased coastal development. So in conclusion, we did find that this shallow water estuary could preserve a record of storms, although there are some uncertainties with the age model. We found that the prehistoric storm record showed more coarse layers that could suggest larger storms in the past. And we also want to identify that these paleo reconstructions are key to providing context to future storm events.